Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In our last class of power electronics, actually we have started a new unit, that is applications of power electronics, and where we have discussed about the speed control of DC motors and different DC motors, separately excited DC motors, and all types of DC motors were being covered in the last class. Actually, the speed control of different DC motor. So basically, we have covered all these drives for controlling DC motor speed control. So that is. In the last class we have covered different methods of speed control, and where we have used single phase separately excited drives, also single phase half wave converter drives, and single phase pool converter drives, and DC chopper drives. Okay, so today actually we will start up another topics, that is of course of speed control, that is speed control of AC motors. Okay, so whenever we are going to discuss about the speed control methods of various types of speed control motors, particularly DC and AC motors, so we definitely will cover this portions, that is basically with a brief introduction we can go to the direct of this speed control of various speed control motors. Actually we have already covered the speed control of DC motors. Basically a large number of motors are being used for general purpose in our surroundings, from household equipment to machine tools in industrial facilities, and the electric motor is now a necessary and indispensable source of power in many industries, and the function and performance required for these motors are wide ranging. When focusing attention on the speed control segment of the motor market, some servo and stepper motors control their speed with a pulse trend, while the induction motor and the brushless DC motor control speed with an external register and or DC voltage. And particularly in this discussions, so we will explain in short the structures, the speed control principle, and features of the following three group of drives, that is that can control the speed relatively easily by using an analog input. And AC speed control motor and gear motors, and brushless DC motors and gear motors, and particularly inverter units, which is most essential for the speed controls of the AC motors. So basically in short we'll go through this, then we'll discuss one after another speed control methods of various speed control motors, and basically the output control methods of a speed control circuit can be divided roughly into two groups, that is phase control and inverter control, which make up product groups, that is like here. So output control method, either phase control or inverter control. So that is classifications of this output control method, that is phase control, single phase induction motor, AC speed control motor. So these are the products of the different companies available in the market. And inverter control may be brushless DC motors, and three-phase induction motors, and brushless DC motor unit, then under the brushless DC motor, and three-phase induction motor under the inverter unit. So this is the classifications of speed control motors. And AC speed control method, under this if we go to a very quick and short discussion, so which we have already studied in our electric machine purpose, so that is the AC speed control motors. Constructions of these motors are like this. This is shown in this figure. So this is the construction of the single phase and three-phase induction motors. Includes starter, where the primary winding is wound and basket shaft, and solid aluminum die-cast rotor. The rotor is low cost because the structure is simple and does not use magnet. Okay, so this is basically the figure of this say three-phase actually induction motor construction, whether it is three-phase or single-phase, so construction is more or less the same in lookout. Only the difference is the stator winding is of course of three-phase distributed winding. So this is motor case, and say basically this is stator, this is rotor, this is bearing, this is the actually bracket, output shaft. Say this is actually say lead wires. Okay, so this is mainly the construction, and when the speed of this motor is to be controlled, a Tacho generator is used to detect the speed and is attached to the motor that is shown here in this figure, the AC speed control motor systems. So this is power supply, this is motor, this is Tacho generator, and this is comparators. Okay, this is the potentiometer actually. This is the speed control pack. Okay, this is the capacitor. So basically speed of this motor is controlled. Tacho generator is used to detect the speed and is attached to the motor that is shown here. And the Tacho generator is made of a magnet connected directly to the motor shaft and the starter coil that detects the magnetic poles and generates an AC voltage at 12 cycles per volt revolution. And since this voltage and frequency increase with the rise of the rotational speed, the rotational speed of the motor is controlled based on this signal. Okay, so now we'll go to the principle of the speed control. So rotational speed N of an induction motor can be shown by this expression. So this is the rotational speed N of an induction motor. When the voltage applied to the motor is increased and decreased, the slip S changes. When the rotational speed N will also change. So this is a revolution per minute in N. This is frequency F, the small of course in hertz. Number of poles of the motor, AC is the slip. And in the case of an induction motor, so that is as shown here, this is the speed torque characteristics of the induction motor. So a stable range and an unstable range exists in the rotational speed torque curve. See, this is the stable range and this is the unstable range of speed torque curve. So basically since it is impossible to reliably operate in the unstable region range, simple voltage control or open loop control is limited to controlling the speed in a narrow range, say like N1 to N3, which is shown in this figure. Okay, this is in figure 3. Actually in the narrow range, figure 4, this is actually okay. So this speed control range is very narrow. Okay, so this one actually. Okay, so now basically to make it possible to operate reliably even in the above mentioned unstable range, it is necessary to detect so with the rotational speed of the motor and use a voltage control mechanism that is called closed loop control that reduces the speed error when compared to a set value. So that is actually shown here. So this is the simple voltage control method, and available voltage control methods include control by a transformer or by phase control. It is shown in figure 6, voltage control by transformer. This is the control voltage by modulating amplitude of the voltage. Okay, so this is voltage control voltage change by transformer basically. So this is shown when the voltage is controlled by using a transformer. This method is not so easy to do with an AC speed control motor. So alternatively, the AC voltage can be adjusted by setting the on-off time of every half cycle of the AC voltage, that is whether it is 50 Hz or 60 Hz, applied to the motor using switching element, thyristor or track, and that can directly turn on and off the AC voltage. So that is shown in figure 7 and 8. So see control voltage lengthening up periods, and this is shown. This is track control circuit. Okay, so basically what we are getting, speed control is obtained by the phase control method by controlling the RMS value of AC voltage. Okay, so this is shown in this figure, figure 7 and 8. This is a track control unit, and this AC speed control method can provide steady speed control by closed loop phase control even in the unstable range. And in this figure 9 shows the configuration of the speed control system for an, let's say, AC speed control motor in a block diagram. So this is the motor, this is the power supply, this is synchronized supply voltage, then triangular wave, this is comparison unit, this is the phase control unit. Actually this is the detected voltage of the motors, this is the speed setting. Okay, then comparison circuit, then phase control, and this is the block diagram of the AC speed control motor system. Okay, now if we go this is the waveforms for each block, that is the power supply and the voltage signal. This is power supply, this is voltage signal, and this is the triangular wave, this is the gate trigger, this is single synchronized supply voltage, and this motor supply voltage. Okay, that is actually shown in the block diagram, and this is the corresponding say waveform. Okay, so this figure shows the waveforms of each block, and the speed set value D, that is here, speed set value D. Yes, this is speed setting, and the speed set value D and the detected value E of the speed generated by a Tacho generator is compared in the comparison amplifier block, and then the level of the voltage signal A is determined, that is here. Okay, shown here, and the voltage signal A is low when the speed detected value to the speed set value rises, and is higher when the speed set value lowers. And since the trigger signal is output at the point where the triangular wave say B intersects with voltage signal A, the timing or that is the phase angle when the track is turned on with the level of the voltage signal A is determined when actually when this timing is slow, the voltage applied to the motor becomes low, and the control is repeated, so that the difference between the speed detected value and the speed set value may always be constant. So this is actually the block diagram of AC speed control motor systems, and this is the say waveform for each block. Okay, now actually this figure 11 shows the appearance of the above mentioned this speed control in figure 11. The operation point, the motor draws a loop of QRSTQ centering on O, and rotational speed is maintained between N1 and N2, and this loop is reduced as much as possible by increasing the speed detection accuracy. So this is shown here. So this is the operations of the speed control. Actually this is whatever the discussed, this is shown in this graphical representation. So this is the operation of the speed control, and the AC speed control motor has the say following the features when using this closed loop phase control. And since the AC voltage is controlled directly, the speed control circuit can be configured simply because a smoothing circuit is unnecessary, allowing for a compact design at a low price. Okay, and in the same way a long life design is possible because a large aluminum electrolytic capacitor is unnecessary, and the switching is operated only one time each half cycle of the commercial AC power supply, which keeps the generated noise low. So before going to the characteristics of this speed control, AC speed control, we are once again telling you these different methods, the simple voltage control methods, then speed torque characteristics of induction motor, and how the principle of speed control operates. So from these equations we will get this say speed torque characteristics, then simple voltage control methods, graphical representations of the characteristics at supply voltage, different supply voltage range, okay, load torque characteristics. Then we have say shown, that is the voltage change, that is by transformer, that is control voltage by modulating amplitude of voltage and how it will be set. Then voltage control by phase control we have discussed, and that is graphical representation of this is the waveforms. Then we have shown you this is the track control circuit. Then this is the block diagram of AC speed control motor systems, okay, and this is the waveforms of the different block, that is each block of this block diagram. Then we have discussed this operations principle, operations of this speed control methods, etc. Okay, so next we will discuss this. Now characteristics portions, actually we will discuss about this AC motors speed control. Basically speed control motors generally have the rotational speed torque characteristics, and that is shown in this figure. So this is the speed torque characteristics, rotational speed torque characteristics basically known as. Here we have shown safe operation line. So basically this safe operation line is included in this rotational speed torque characteristics, and this safe operation line depends the limitations where the motor can perform at continuous duty without exceeding its maximum permissible temperatures. So this is actually a safe operation line. Okay, now in case of brushless DC motor speed control unit, this construction of this motor is like this, and brushless motor a coil is stark wet, that is Y wet, with 3 phases U, V and W, and is located in the stator, and the rotor is made of magnet. It's magnetized in a multiple configuration, and that is shown in this figure. Actually this figure, coming to this construction part, and inside the stator 3 Hall ICs are arranged as say magnetic elements, so that the phase difference of the output signal from each Hall IC will be 120 degrees apart from every rotation of the rotors. So this is the construction part, that is say U phase, U winding, say V phase, V winding, and this is W phase, W winding, and rotor actually this is the rotor magnet. Okay, so this is motor windings U, V and W, and these are the Hall ICs. This is Hall effect ICs, so connected in this fashion. So this is the for output 1, this is for output 2, and this is for output 3. Okay, so basically the principle of this speed control, that is a rotational speed torque characteristics of a brushless DC motor, show a negative sloping characteristic when speed is not controlled, which is similar to that of a brushed DC motor. Okay, so this is the rotational speed torque characteristics of the DC motor. So you see, okay. So when no load is applied and input voltage is set at V2, say in this figure, so the operation point of the motor becomes P, okay, and the rotational speed is N1, and when that load torque is say T1, say is applied, the operation point shifts to Q, okay, say from P to Q, and the rotational speed slows to this is N2, okay, N2. However, the rotational speed returns to N1 if the voltage is raised to say V2, V3, okay. So that is actually the point of say return of this rotational speed at n1. Okay, and therefore since the rotational speed changes whenever the load torque changes, the speed control mechanism will only have to change the input voltage whenever a change in the speed is seen in order to maintain a constant speed on the say PR line. Okay, so this voltage control is realized by an inverter in the output part of the control circuit, that is the driver circuit, and this inverter generates a three-phase AC voltage from DC current. Okay, by turning on and off like sequence that is shown in this figure B 16B, by using the 6 switching elements FET or IGBT that is shown in say this figure. Okay, so this is output part of the control circuit or driver, and this is the switching sequence. Okay, the switching elements are connected to the motor winding as shown and in this figure. Okay, this is the switching element connected in the motor winding, and the on-off state of the switching element determines which coil of the stator is energized and in which direction the current will flow, and that is which coil becomes a N pole or a S pole, that is north or south pole. In fact, the position of the rotor's magnetic pole is detected by the Hall IC, and an appropriate switching element is turned on or off, and that is shown in this sequence switching sequence diagram in figure 16B. For example, in case of step 1, the transistors TR1 and TR6 are on, say for step 1. Okay, these two transistors are on or off, say actually that is shown here, and for this is on, and the current flows from U phase to W phase, that is current flows from U phase to W phase. Okay, and at this time U phase is excited as an north pole, and W phase becomes a south pole, and the rotor rotates by 30 degree, moving to step 2. Okay, once one rotation of the rotor is made by repeating these operations 12 times, that is step 1 to 12. Okay, so that is shown here in discussions in this switching table. So this actually this figure 17 shows the configuration of the speed control of a brushless DC motor unit in a block diagram. This is the motor, and basically this is inverter, basically power supply, this is converter, this is inverter and given to the motor, and this is actually proportional detection. This is the peak detection method. This is the speed setting, the speed detection and speed setting. Then it is the comparison amplifier. Then it is PWM setting goes so to for the operation of the inverter. Okay, and this output is given to the motor. Okay, so this is the block diagram of brushless DC motor system, and the switching sequence of the inverter is decided by the signal from the Hall IC in the positional detection part of the block diagram, and the motor rotates. Okay, then the signal from the Hall IC is sent to the speed detector to become a speed signal, and it is compared with the speed setting signal in the comparison amplifier block, which then generates a deviation signal. The value of the motor input current is determined by the PWM setting block based on the deviation signal as I discussed. So brushless DC motor units have the following features. It has high efficiency because of permanent magnet rotor is used, and secondary loss is small, and rotor inertia can be reduced, and a high speed response is obtained. Okay, and it is possible to downsize the motor because it is highly efficient, and speed fluctuation with changing loads is low. And in this figure 16 basically shows a typical switching sequence of 120 degree energy method, and even more efficient brushless DC motor system uses a sine wave method by obtaining high resolution rotor position information from software from the Hall IC signal, and this method results in low noise drive method, since the current that flows to the motor does not change rapidly. So this is the comparisons of the voltage applied by the sine wave drive method and 120-degree drive method. This is shown in this figure 18. And the characteristics part, the rotational speed torque characteristics of a brushless DC motor system have a limited duty region in addition to the continuous operation area, and the limited duty operation area is very effective when starting an inertial load. However, when operation in the limited duty region is continued for 5 seconds or more, the diverse overload protection function is activated, and the motor decelerates to a stop. So an inverter speed control unit, in here the principle of speed control is like this. The inverter unit controls the speed of a 3-phase induction motor by changing the frequency F of the voltage applied to the motor, and the inverter unit changes the frequency F by changing on-off cycle of the 6 switching elements, and the rotational speed N of the motor changes in proportion to the expressions in the formula given here, that is N equal to 120 F into 1 minus S by P. This is rotational speed in revolution per minute, RPM. This is hertz in frequency, and this is the number of poles of the motor, and this is the slip. So in addition to make the voltage applied to the winding have a sine wave shape, the inverter controls the on-off duty cycle, as that is shown in this figure 21. So the on-off time is controlled so that the average voltage applied to the motor becomes a sine wave shape by comparing the triangular wave called a carrier signal with the sine wave shape signal waveform. This method is called PWM control. So we have already discussed this PWM control method during our PWM inverters. This is sine wave shape, this is the carrier signal, and this is the output pulse signal. So this is duty cycle of on-off. Okay. So the speed control methods of our inverter units is divided into 2 types of open loop control that simply changes the speed, and closed loop control that reduces the speed variation with load changes of the motor. And this is the open loop control, and this is shown in this. This is the open loop control. This is actually figure 20. So configuration of the open loop control is block diagram. So this is the motor, and this is the speed setting. This is V by F control, PWM setting of the inverters. This is the power supply, this is converter, and this is the coming to the inverter. Okay, so and this method is used to change the input voltage and the frequency of the motor according to the set frequency. And this method is suitable by changing speed and can obtain high speeds. The frequency can be set up to 80 Hz simply when speed regulation with varying loads is not so much of a concern. And the generative torque of the motor is shown by this formula, T equal to Ki V by F. And from this system it can be said that the torque will also be constant by making V by F and the ratio of the voltage V to the frequency F constant. So this is actually T is the torque in Newton meter, supply voltage in volt, motor current ampere, frequency in hertz, and this is K is the constant. So however the loads lower the speed is, the more difficult it is to keep constant the input impedance of the induction motor with the change in frequency, and therefore to obtain the torque say this, that is constant from low speed to high speed, it is necessary to adjust say V by F ratio at low speed in accordance to the characteristics of the motor, like the solid line shown in this figure. Okay, so this is actually. And for closed loop control, this is the figure, this block diagram of the closed loop control. So again the same thing, this is actually the closed loop phase detection. So this is everything is same except this. Okay, so this method detects the phase difference between the voltage of the inverter output block and the primary current, which calculates the driving frequency corresponding to the load using the characteristics data table. So that is shown here. This is the characteristic data table. So prepared beforehand, and controls the inverter frequency without the need for a speed sensor in the rotor. So this is the data table. So characteristics of this data table, with this characteristics table and the detected phase difference time t, the inverter calculates an inverter output frequency that corresponds to the rotational speed command and set by the speed potentiometer, and outputs it is the inverter output frequency. And after receiving the output frequency, the V/F control block calculates the voltage applied to the motor corresponding to the output frequency F, and performs the speed control by driving the PWM inverter. And as a result, when the load is applied, the output frequency of the inverter is boosted so that the decrease in the rotational speed may be compensated. Okay, so this characteristics of this rotational speed torque characteristics of the inverter is shown here in these figures, and is explained in the AC motor speed control section. A safe operation line is drawn on the torque characteristics, and this line represents the limit of the continuous operation, and the area under this line is called the continuous operation area. So this is shown here. So it will be safe line. Okay, and this is rotational speed torque characteristics for the closed loop motor. So we can summarize this. These three AC speed control motors, brushless DC motors controls, and inverter units are for use in a wide range of speed control applications, and the proper speed control product can be selected according to the function and the performance and the cost of the purpose desired for the applications. So that's all. These are the reference of this curriculum. So thank you very much for